All right, we should be recording. So yeah, this is the pre-processing lecture. I hinted that this is the second most important lecture of the semester because this is really what you unfortunately spend most of your time doing as an AI for EO researcher. 90% of the work is getting the data into an AI-ready format. The AI that comes after is actually relatively easy compared to the pre-processing that comes first. Administrative things, I now have grades for everyone for homework 0 and homework 1. I hopefully gave useful feedback on those. If you have any questions on your feedback, let me know. Before, after lecture, office hours, etc. I was going to show the solutions for homework 2 today, but there's at least a couple students who need an extension, so I'll show those next week. The other thing, so I put up a survey on Moodle for basically the first 3 weeks. So the first 3 lectures and the first 3 homework assignments now that you're starting to get grades back for those. And that gives you a chance to say what you liked, what you didn't like with the homeworks, with the lectures. Did things go too quickly, too slow, etc. And then also, we were joking about this earlier. We have 25 students enrolled, and there is 1 student in the lecture room today. And I don't know if that's because Autobrune is very hard to get to, or because the videos on YouTube are much easier to get to, or because the lectures aren't useful. So I do have a specific question in the feedback survey asking, like, what can I do to convince people to come to lecture? I do think that there's value in in-person interaction, questions, answers, in-person attendance. And if by any chance, unfortunately likely chance, there's 0 people in lecture, I'm not gonna record the lecture, I'm not gonna talk to an empty room. So I would like to get more people attending in lecture. I know there's a couple people who are sick or injured or who are working and have a conflict with this time. That's completely fine, just let me know in the feedback survey. It's completely anonymous, so feel free to complain about me, say I'm the worst teacher ever, I don't mind. As long as it's constructive. If I'm bad, tell me what I can improve. But we'll go over the results of that survey next week in lecture, so do try to finish this before next Monday. That should be up on Moodle now. So contents that we're going to cover today, we're going to be covering basically anything you need to know about data handling and data preprocessing, all the way down to low-level tools like GDAL and higher-level tools that you can use to interact with different types of data. Different kinds of file formats, compression, etc. that you might encounter, how to do things like reprojection and resampling, and then the exact preprocessing pipeline that a lot of the data that you work with already went through, how you can also reproduce some of those steps manually yourself. Okay, so the first thing that is worth mentioning is that in the world of images, there are 2 kinds of images that you will see constantly. There are raster images and vector images. If you're looking at traditional file formats, those are things like JPEG, GIF, PNG. When you take a picture with your cell phone, you get a JPEG, most likely, because that one has a little bit better compression than PNG. These work really, really well for natural scenes because you can't zoom in forever. There's a limit to how much information you can record. And except for urban environments where there happen to be a lot of straight lines, the natural world is mostly organic. There aren't necessarily underlying structures, objects, polygons, lines in the natural world that you could record. Whereas vector data, this is file formats like SVG, PDF. These work really well for things that can be represented mathematically. So you can have a curve that has a radius and a length, or you can have a line that has a start point and an end point. This works really well for certain other kinds of data that you know has certain limitations. So for example, this building outside, if I want to know the building footprint from space, this satellite image that I take of this building is going to be pixelated. It's going to be very blocky. But when I'm manually labeling these things, or I'm trying to make labels, I know that it's going to be approximately a rectangle. And I know that even though it looks like a jagged line in the image, that's actually a straight diagonal line. In the world of Earth observation, raster file formats like GeoTIFF are commonly used for things like satellite imagery, model inputs, whereas vector file formats are more commonly used for model outputs, where you're actually trying to make a map of the Earth. You start with a real map, and real maps typically have these vector formats. The benefit of vector is you can zoom in forever, and it always stays very sharp and crisp because it's defined by math, not by pixels. But you frequently need to be able to convert back and forth between these two file formats, and I'll show how to do that today. The other thing that we've mentioned a couple times, you saw it in Homework 0 extra credit, and then you saw it a little bit 2 lectures ago, is this GDAL thing. And I hinted that GDAL is really important, but I didn't really talk about how and why and the history behind it. So GDAL really is the core library for all of GIS. Every GIS tool that you've ever used is built on top of GDAL. Everyone and everything uses GDAL under the hood. Even if you don't realize it, you've already used GDAL several times on the last homework assignment. For historical reasons, there were actually 2 libraries. GDAL, Geographic Data Abstraction Library, this started off working only on raster files. So things like satellite images, how do I do reprojection, cropping, etc. for these multispectral images? And then there was a separate library, OGR, that did vector file formats. And you can imagine how raster files and vector files are completely different. All of the internals are very different for these 2 tools. Over time, these 2 actually unified into one library. So when you install GDAL, you actually get both of these 2 things. You get GDAL and OGR, and both are maintained by the Open Source Geospatial Foundation because they're really pivotal to the entire GIS ecosystem. GDAL itself and OGR as well, these are mostly written in C++. So very, very fast, not so user-friendly. For us as data scientists, we don't care so much about the speed as long as the hard parts are optimized and written in very fast code, and then we can access the slow parts with Python, and then we don't have to worry about speed. So things like preprocessing, regardless of what you do it in, it's actually using GDAL to do it, where it's fast, and then it's converting it back to Python so that you can interact with it in your traditional data science pipeline. There are actually several different Python libraries that you can use to interact with GDAL. So when I started using GDAL, I think it was 2013, there was no Python interface. Python was not really that popular at the time. It had started to take off in the computer science world, but not really in the GIS world so much. So in 2013, we were actually running GDAL commands with, I think Python subprocess didn't exist yet, so it was like os.popen, and you had to run the GDAL command through the Python thing and then parse the output manually, and it was an absolute nightmare. Sometime after that, the beautiful folks at GDAL decided we can just generate Python bindings for the whole library, and then you can interact with every single built-in function that you could from the command line or from a C++ library in Python. And it will be just as fast and beautiful. So they're using a tool called Swig that lets you basically generate Python bindings for a C++ library. There's also bindings for Perl, which I think they might have removed, and JavaScript, which they still have, but everything's Python in this course. 2 downsides of OSGeo. Because it's auto-generated based on the C++ API, it feels a lot like C++. So a lot of the things that you're used to in Python in terms of how things are named, what style things use, what the documentation looks like, but also what happens when there's an error message, things are completely different in C++. So for example, if you use OSGeo and there's an error, it will tell you there was an error, and then it will continue with the rest of your code, which obviously won't work because there was an error ahead. So the OSGeo bindings are not for the faint of heart, but they are very powerful, and there are things that they can do that these other libraries can't do. On top of GDAL, there are also two popular handcrafted Python bindings. They don't cover all of the features of GDAL, but they cover most of the important ones. So these are raster.io for the raster implementations, and then either Fiona or PyOGR.io for the vector implementations. So these are, again, relatively low level. You're using these to do small operations on raster files or vector files, things like cropping, things like resizing. But they work very, very well. And also, they're much easier to install. As you've probably seen with GDAL, it's not so easy to get installed. You had an extra credit where you had to compile it from source, but you don't have to do that for this course. You can install it with Conda, Homebrew, etc. But I also had students who had problems with that a couple weeks ago too. So GDAL is a little tricky to install. There are no pre-compiled binaries on PyPy, so you can't just pip install it. Whereas raster.io, Fiona, PyOGR.io, you can pip install these and move on, and it's quite nice. And then there are two popular higher level abstractions on top of this. If you want to use things like geotiff data in the Xarray ecosystem, you can use a library called Rio Xarray, which combines raster.io and Xarray. And then if you want to use some of these vector bindings in the pandas ecosystem, there's a library called GeoPandas, which used to depend on Fiona and now depends on PyOGR.io. These are quite high level abstractions, so you can do very powerful things very quickly with very little code. I want to teach you both though. I want to teach you both the low level raster.io Fiona style of manipulating files and the higher level Rio Xarray GeoPandas style, so that you know what GeoPandas is doing behind the scenes without just treating it as magic. So what does GDAL do? What makes GDAL so popular? The real reason that GDAL was very successful is it kept a fixed set of features that have slowly grown over time, core features that it implements, and then it had built-in drivers for hundreds of file formats. Compared to your phone camera, where things are usually JPEG, or maybe Apple's favorite file format that they invented, in satellite imagery, every satellite has a different file format. Everyone is constantly inventing new file formats for satellite imagery. This is only a small number of them that you can and will see over your career. There's 160 plus drivers at the moment. They're constantly changing. So I think like GRASS support was removed and 5 other file drivers were added in a couple of releases ago. So this is constantly changing. These are just for raster files. OGR has another 80 vector driver file formats. So if you want to load things like GeoJSONs, shapefiles, OpenStreetMap data, etc., you can also load all of these directly in the same kind of API. So by having this kind of component-based plug-and-play ecosystem, with GDAL, all of a sudden, one library can interact with hundreds of file formats, and you don't really need to worry about the details of, is this a TIFF file, or is this a ZAR file, or is this an HTF5 file? It's the same command regardless. The other thing that is really worth knowing is how your data is structured internally. So if you've taken the image processing course here at TUM, we've talked about this a little bit as well. But basically, when you store data on a computer, that data is not stored in 2D or 3D, it's stored in 1D. You have a very long list of numbers. Every number is that pixel and that color. So one XY location and color channel location stored in a vector. You can store this vector in many different ways. As you saw from homework 2, most of these satellite images are very large. There may be 10,000 by 10,000 pixels, so 100 million pixels in total for each color. So if you've got another 10 bands, that's 1 billion pixels in one image. We don't really want to store things in like thousands of tiny little images, but we can also rearrange the internal structure of that data to make it easier to load. When we're doing machine learning, we never want to load the entire image and throw it on our GPU and pass it through a machine learning model. It's just too big, especially when there's millions of images. What we usually do instead is chop out small little windows and read that window for our model training. Now, most images are stored like the image on the right, where you've got a row for every X location or every Y location stored in the computer. And if you want to load that little area in red, you have to read the entire row from disk into memory and then chop it down to the region of interest. One of the popular ways of storing geotiffs, especially for cloud computing, is what is known as a cloud optimized geotiff or COG specification, which basically says if we can store the data in blocks, we only need to load the blocks that we need as opposed to the entire row. Especially when you're making a very large mosaic that could cover the entire Earth, you don't want to read an entire row just to look at one city. You only want to load the blocks that you need to. So storing your data in blocks like this can help a lot with file I/O performance. The other thing that is definitely very different from traditional computer vision is things like coordinate reference systems and reprojection. So hopefully, as you all know, the Earth is 3D, but our images that we're taking are 2D. So we need some sort of projection to go from a 3D surface onto a 2D image, and we need some sort of coordinate reference system to go back from that 2D image to a map of the Earth where you can correctly geolocate things. There are thousands of different projections and coordinate reference systems that are used, and there's no real common standards here because it depends on what you're trying to optimize for. For example, you've probably seen this Mercator projection before. This is what you get when you open Google Maps and you zoom in. And for most people, this is what the Earth looks like. But is this actually what the Earth looks like? So the shape of all of these continents and land masses looks correct. The size does not. So in this image, it looks like Africa and Greenland are about the same size, right? This is the image that we show all of our children when they're learning, here's a map of the Earth, look at how big Greenland is. In reality, it looks a little bit closer to this. So Africa is 15 times larger than Greenland. The Mercator projection is what is known as an equal angle, but not equal area projection. So all of the shapes look correct, all of the angles look correct. If you go from here west this far, you get to this new destination. But everything's distorted in order to stretch a 3D surface onto a 2D plane. The top projection, Elber's equal area, is the opposite. This is an equal area projection, but not an equal angle projection. So things near the poles get very squished vertically, but the area is correct. That's the actual size of Greenland compared to Africa. Africa is actually extremely large compared to most other continents, except maybe Eurasia. And there's everything you can dream of in between. You can have ones where you sacrifice water in order to have the least amount of distortion for land masses. There's also the reverse. So if you're a fish and you care more about ocean mapping than you do about land mapping, you can get a reverse good sign that cuts up land masses in order to make the ocean less distorted. And all of these can be specifically located where you say, I actually care only about Germany. I would like to ensure that Germany has the least amount of distortion possible. And if you zoom out for the whole world, it's going to look awful. But if you're only focusing on Germany, it has the perfect image with the least amount of distortion for that region. So you can build infinitely many projections for specific locations to avoid reprojection artifacts. But if you're looking at global projections, you're always going to have some sort of artifacts. And frequently, your data will be stored in one or many of these different CRSs, and you need to reproject them so that they're all in the same CRS. Otherwise, you load two images and one is distorted with respect to the other. The other thing that you always need to keep in mind is the image resolution. So let's say we have a situation like this. The black grid, this is our image. Those are all the pixels in our grid. We would like to build a machine learning model that maps from this image input to a mask output. Unfortunately, the mask in red has a completely different resolution than my input image. So even though they're in the same coordinate reference system, even though the grids aren't rotated with respect to each other, they don't have a one-to-one matching between input pixel and output pixel. If you want to train a machine learning model to go from A to B, you need A and B to line up, right? You can't have things off by half a pixel or 2 pixels, etc. So here we would either need to resample our red grid to match the black grid, or vice versa. It depends on what our final goal is. The other situation that you can end up in is even if both of your grids have the exact same resolution, they might be off by half a pixel, or a tenth of a pixel, or a 1/100th of a pixel. And as a result, you still don't have that one-to-one mapping between input pixel and output pixel. So in this case, you have the same resolution, but you don't have TAP, target aligned pixels. So you can specifically tell GDAL that, yes, I want this to have the same resolution and I want it to have the same underlying grid that's not off by half a pixel in order to ensure that you do have a one-to-one mapping. There's all kinds of other details of GDAL that you can get into, for example, things like file compression. There's many different options here that GDAL supports, and they all have trade-offs of, are you willing to have very slow compression time in exchange for very good compression, where it's a much smaller file? What is the time required to compress versus the time required to decompress? Is the file format open source, or is it some paid service? So there's a lot of different compression options with very different speeds and different levels of fidelity, but they're mostly, some of these are lossless, but most of these are lossy. So you're assuming that you lose a little bit, maybe 1% of the data, in order to chop the file size down by 30% or more. The other thing I want to provide as motivation here is why we're really doing this. So there's a lot of reasons why we need to pre-process data. The end goal is machine learning, at least in this course. And pre-processing is really just the process of getting your data to be in a machine learning ready format. So in addition to all of the things that I've already shown you, including coordinate systems and resolution, there's also differences in data, such as what if you have categorical data as opposed to images? What if you have text data? What if you have missing data or inconsistent data? So these are all things that prevent you from doing machine learning. Machine learning doesn't know what to do with a NaN. It doesn't know what to do with a sentence. You need to convert everything to numbers in order for machine learning to be able to understand it. So what we do in pre-processing is basically manipulating the data to get it into this uniform ML-ready format. Everything needs to have a numerical representation. So we can't have categories, we can't have text, we can't have NaNs, we can't have unknown time, we can't have corrupted file. All of these things would prevent us from doing any machine learning. And pre-processing is usually done only once, and it's done for all of our data. So regardless of whether we're doing train, validation, test, we always need to do pre-processing, otherwise the data is not in the right format. Later in the course, I think like the second to last or third to last lecture, we'll also learn about data augmentation. It sounds very similar, you're manipulating data, but it's not to get data to be an ML-ready format, it's to artificially increase the size of your data set. That you only do during training, whereas pre-processing you always do. So for now, focus on pre-processing. We'll talk about data augmentation in a few weeks. The other thing that I want to make clear is how much work goes into pre-processing your data before you even start using it. So when a satellite takes an image, and when you download the image, there's a lot of work that goes on behind the scenes by the great folks at NASA, ESA, USGS, other space agencies, DLR, et cetera, that ensures that the data is of the highest quality before you even get to use it. So I want to quickly walk through some of these. I really hope that you never have to do any of these because they are not easy. But there are definitely situations when you need to do this. I've, in fact, needed to do this myself. I was working on a research project in the Arctic. And at the time, at least 10 years ago, we didn't have good elevation models for the Arctic. And so if you've got imagery of the Arctic, it was kind of like plus or minus a kilometer in space and distortion, and you couldn't really use it without manually doing many of these steps. So nowadays things are much better than they used to be, but there are still situations where you might need to do these yourself, and it's worth knowing what people are doing for you. So the first thing that we need to do to go from a level 0 product to a level 1 product is radiometric calibration. So our satellite is a sensor up in space. It's got a photon counter that counts the number of photons of different wavelengths that hit the sensor. There's not really physical units for this, and depending on how long you leave the shutter open, for instance, all of your numbers change, but that doesn't change the brightness of the object that it's trying to record. So we would like to calibrate our sensor and get actual physical units of radiance from our image. Usually what you do is you build your sensor in a lab, you calibrate it in a factory against some reference standard. So you've got like a bunch of templated images that it takes a picture of, and then it says, okay, this is perfect black, this is perfect white, these are different colors. Let's balance everything out so that the image looks similar to the reality. And then once you launch it into space, it's much harder to do these things, and sensors naturally drift out of focus over time. So there's also onboard calibration where you either have reference images on the Earth, like very large buildings that just have a specific image painted on top in order to calibrate the satellite, or you calibrate your satellite for the current time against past time from the same satellite. This is the math. There's a lot of physics involved here. So there is things related to both the angle of sunlight hitting the Earth and the angle of light bouncing off of Earth and hitting the satellite, rescaling factors, additive factors, quantization factors, etc. But if you do all this correctly and you put a lot of hard work into it, you get a very good calibrated sensor that is comparable to other sensors, at least for those wavelengths. The next thing that you need to do to get to level 1 is geometric correction. So we'll see this later, so I won't go into too much detail now. I've got a nice video to show of how this works. But basically, when you take an image, the satellite is flying over the Earth, and you have some altimetry data. So you know approximately where the satellite is, approximately what angle the satellite is looking at the ground with, approximately what angle the sun is, and you can kind of locate things plus or minus 100 meters or a kilometer. And for many applications, that's fine. You get an image, you say, oh, yep, that's the city I'm interested in. Let's see how things are doing. But if you want to compare before and after, you need that one-to-one mapping between input pixel and the next input pixel. They need to perfectly line up. You can't have plus or minus a kilometer in your data. So that's where geometric correction comes in. Basically what you do is you have a bunch of ground control points where you know the exact location, probably based on some sort of GPS sensor, and you map your image. You find the same locations in that image, and you warp your image to fit it. If you've ever done something like making a panorama on your phone, it's the exact same process. You look for points that aren't blurry shapes, but hard corners and edges, and you make sure they line up in every image so that when you stack them together, you get one large map. So this will get us to a level 2 top of atmosphere product, perfectly located somewhere on the ground, but there's still a lot of noise in the data.
So that's the ones we downloaded, right?
We downloaded level 2, so surface reflectance. But yes, you can also download level 1. That's quite commonly used. The next thing that we do is cloud removal. So any satellite image that you take probably has at least a few clouds in it. at the very least, you would like to know where the clouds are. So for example, in the top image, there are many bright white, clear, cloudy pixels. There are many black cloud shadow pixels. And then there's also thin cloud pixels, which are even harder to detect. You can see I did a little bit of prediction there and did a little bit better with thin clouds. But I completely missed all of the cloud shadow, unfortunately, in my model. So we would like to be able to map at least what is cloud, thin cloud, cloud shadow, and clear, reliable image that we can use for machine learning. We also have to worry about things like snow and ice and whether those are messing things up. And this is that quality assurance band that we saw 2 weeks ago. This is used to store that information. There's many different ways to do this. You can do thresholding, which is what people did traditionally. There's also a lot of research on deep learning for making good cloud masks. The next step then would be cloud removal, where you try to fill in the gaps. I'll talk about that later. The next thing we want to do, we want to convert from our top of atmosphere radiance, how much light is leaving the atmosphere of the Earth, to actual surface reflectance. So this accounts for things like aerosols in the atmosphere that scatter light, or in general, atmospheric effects that distort the color of the image. What you see here, the black line is the amount of light emitted by the Earth. And the green line is the amount of scattering as a result of atmospheric effects. So it depends a lot on the wavelength of the light on the bottom axis. That really determines whether or not there are certain molecules like aerosols that might interact with that wavelength of light. So again, very physics-based. You have to understand the relationship between radiance from the atmosphere and actual reflectance from the surface. But what you get if you do this correctly is a very crisp and clear image of what the Earth looks like at the ground level without any atmospheric distortion, haze, aerosol scattering, etc. So this gets us to our surface reflectance product. And then the final thing that can be important depending on your region is topographic correction. So especially in mountainous regions such as the Alps. If you take an image with a satellite and the satellite is not perfectly straight down for every pixel, not even for the middle, you get warping due to the effects of topography. So you get an image like this. The raw imagery looks perfectly flat, but you have some sort of known elevation model where you project that image on top and then you get slight corrections, slight shift between the two on the order of even just a few pixels. But a few pixels can be a huge difference if you're looking for something like a landslide in a mountainous region. The other kind of topographic correction that we do is called bidirectional reflectance distribution function, BRDF. So imagine a situation like this. You have light shining from the sun at some angle and bouncing towards a sensor at some other angle. Depending on those two angles, the surface of the Earth may look completely different. So here are some actual images of this. You should be able to tell which one the light is in front of you versus which one the light is behind you. So on the left one, the light is actually behind you. So you can see this side of this forest or this soybean field or this dirt very, very clearly. Whereas if the light is away from you, then you see a lot more shadow for the exact same object at the exact same angle. So the angle of the light is extremely important for what things look like. And we don't want that to affect our images. We would like our images to be comparable regardless of where or when they were taken. So there's a lot of math that needs to go into correcting for this in order to ensure that all the colors remain the same regardless of location. So I want to quickly show some of these videos because I think they're really good examples that explain this better than I can. They're like 2 minutes each. They're about 10 years old, so some of the color schemes might be a little bit 90s or 2010s, but hopefully they're useful. The audio is working good.
RMSE is the root mean square error, and it's used to define how spatially accurate an image is.
Landsat collections data is processed to minimize this error, in most cases to less than a third of a pixel.
When we process a satellite image, the first thing we do is we generate a satellite model. Landsat 8 has GPS built in it, so we know we can get the accuracy of that model very tight. For the older sensors, we didn't have that luxury. So when you do systematic model of where those satellites pointing on the ground, the scene can be shifted some. So what we've done is built a ground control library. We have this stack of GCPs that we correlate each image to.
Ground control points are chips which are pulled from a reference grid. Each of these chips are small images in their own rights, which we have precisely located with the Earth's surface. We take the images, we compare them against those hundreds of ground control points for each image, and we shift the data sets so that they align with the ground control points.
After the image is shifted, an RMSE can be determined. 90% of collection scenes are within a 12-meter RMSE goal.
The pixel that we're working with is a 30-meter pixel. So when we say RMSE, we're comparing that image to those points on the ground to ensure that the image actually aligns to that 12-meter specification of each pixel. That way, when you're doing land change monitoring and you're stacking scenes over time, you know that each pixel isn't going to shift more than 12 meters either way.
Each Landsat scene's metadata file contains its RMSE.
This is
Users
that
can also
MTL
choose
file.
an RMSE range in Earth Explorer to narrow their search and get only the scenes that fit their needs.
All right. So yep.
Did they collect the GCP points? Because they have to have accurate images in the beginning, right?
Yep.
How do they do that?
So you basically just look for specific objects that are very clear and obvious, such as the corner of a building or the peak of a mountain, or rivers are bad. Don't use rivers because rivers move. But everything else, like solid rock land masses, where it's very clear where something is, you either go there in person with a GPS sensor or you put a GPS sensor there, and now you know the location of that point. And then you take your reference image, you look for that same very visible, very clear object, and if you have enough of them, not just one, you can perfectly shift things to match up with that. So there's a lot of hard work that goes into it. They said 12 meters, that's like a third of a pixel, right? So they're taking a 30-meter pixel and they're shifting it by a fraction of a pixel to make sure it's perfectly located. So there's a lot of work that goes into that. This is the next video. This kind of explains some of the stuff that we talked about when we were downloading.
Within the Landsat collections, scenes are evaluated and categorized into one of 3 tiers.
The first tier is called real time, and into the real time tier goes all the data immediately after acquisition. And they're left there until such time as final calibration can be applied to those data sets.
The real-time tier holds newly acquired imagery. This can be useful when monitoring events and natural disasters, where near real-time data is critical. Real-time Landsat 8 OLI data is very accurate. However, the thermal bands require additional processing before the scene is placed into the final tier. This processing is applied within 16 days after acquisition. Landsat 7 instrument trending and characterization is applied within 26 days after acquisition, before the data is moved to the final tier.
At that point in time, RMSE is used to determine which of either Tier 1 or Tier 2 those data go into. And we have an RMSE threshold of 12 meters, which dictates whether it goes into Tier 1 or Tier 2.
A large majority of new Landsat scenes meet the requirements to be placed into the higher quality Tier 1. Some scenes, especially those from previous satellites, fall short of the 12-meter RMSE goal and are categorized into Tier 2. These scenes are still valuable in whole or in part, but can be quickly filtered out by users wanting only the best spatial quality. Users interested in Tier 2 scenes can analyze the RMSE and other properties to determine their suitability.
So it lets the user easily be able to go through the archive and pick high quality data that really stacks over time. And they know that the provenance is consistent, the data is processed in a consistent manner, and it has a specific quality to the data.
Landsat Collection 1 is the highest quality inventory of Landsat Level 1 products ever created. This structure ensures that Landsat data products provide a consistent archive of known quality to support time series analyses and data stacking, while controlling continuous improvement of the archive and access to all data as they are acquired.
I think they're on collection 2 now. They reprocessed the entire library to have a new uniform file name format and a lot more metadata provenance. But otherwise, this is still completely relevant. You still get these same options when you go onto Earth Explorer and download your data. And let's skip this one. I'll leave the link to this in the slides and in the reading suggestions. But if you want to learn more about the level 3 products after surface reflectance, things like NDVI, things like land cover maps, this one covers some of the science products quite well. Okay. So that was multispectral processing. What about hyperspectral data? So hyperspectral data is basically, well, we talked about this a little bit 2 weeks ago. Hyperspectral data is closer to a mass spectrometer, where it's actually measuring every wavelength, not just a finite number, and it can be used for differentiating things that otherwise look very similar, like different species of trees that are all more or less green, but have different shades of green, especially when you look at very minute wavelengths. For processing hyperspectral imagery, you basically have to do all the same steps that we just did for multispectral, plus more stuff as a result of how the data is formatted. And this is often something that you as a user still needs to do. This part is not necessarily done for you. So this is also important if you want to ever get into hyperspectral data. Compared to traditional RGB cameras, multispectral and especially hyperspectral, you're measuring a very, very narrow wavelength of light. And so as a result of random chance, how long you have your sensor shutter open for, you get plus or minus 10 photons. And if that's a very narrow wavelength, you can get a very high signal to noise ratio where you actually end up with a lot of noise in your data. This can be thermal noise, quantization noise, or photon noise. There are many kinds of noise in this data, but it tends to be much more noisy than traditional cameras. For denoising, there are many different approaches to doing this. You can even just do something as simple as adding a simple Gaussian blur to make the whole image more smoothed out, and that gets rid of a lot of the noise, but it also gets rid of a lot of the details that you're really interested in capturing. There's other things like this non-local meets global algorithm that can be used. A lot of these algorithms are iterative, so you don't just run them once and you get an answer, you run it until it stops changing something, and then you get your final answer. So I won't go into the details of this, but if you're curious, that's what it's called. That's what most people use for that level of preprocessing. Here's the actual details. It's actually quite detailed. Most of these things involve SVD behind the scenes. And then you use the eigenvalues or eigenvectors accordingly. Another thing that you might want to do is pan sharpening. We won't talk too much about super resolution in this course, but basically what you're doing is you're trying to zoom in and make your image bigger. So especially when you're trying to capture a very narrow wavelength of light, the sacrifice you make is you capture a very large area of the Earth, and then hopefully you get more photons and less noise. But by capturing a very large area, you don't have very much detail. So you get images like this that are extremely blurry. So if you have two satellites, one that is multispectral, where you've got high spatial resolution but low spectral resolution, and a hyperspectral image where you've got the reverse, you can actually combine the two to get a high resolution hyperspectral image. Again, This uses CNMF. There's other techniques that you can use here. There's also a lot of research in how you can use deep learning for this. But you can actually zoom in your image in this way. And this is commonly called pan sharpening because a lot of the satellites that we work with, including Landsat, have what's known as a panchromatic band, where for one specific band of the satellite, they measure a very large swath of wavelengths, maybe the entire visible spectrum. So it's one very large grayscale image of the Earth, but it's very, very high resolution. So for Landsat, it's 15 meter as opposed to 30. So you can take that 15 meter resolution panchromatic band, and you can sharpen the other 30 meter bands, or even I think the thermal is 60 meter resolution. So you can sharpen those using that. But this also works with two different satellites, multispectral and hyperspectral, assuming that the images were approximately taken at the same time, which is never actually the case. You have to get lucky. Another thing that you might encounter is you actually have too much data, and most of it is redundant. So with hyperspectral satellites, we've got 250 spectral bands. If you remember the math that we did earlier, where we've got an image that's 10,000 pixels by 10,000 pixels, with 10 bands, that was only a billion pixels, what did we say? Yeah. With 250, we've got 25 billion pixels that we need to work with. So this is a very large big data problem. And most of this data is actually redundant. So if you have two spectral bands that are really, really close to each other, one might be slightly higher than another, but it's going to be more or less smooth. There's not going to be very large jumps in the spectra. So there's a lot of correlation between neighboring bands. And then also, most of the bands aren't useful at all for this specific application. So remember, multispectral satellites, we capture the wavelengths we know are important, and we use them for known applications. Hyperspectral satellites, we capture every wavelength, and we look for new applications that we never even dreamed of before because we never had access to this data before. So we've got a lot of data, most of it's useless, and there's a lot of correlation between bands. There's several different techniques for dimensionality reduction. So traditionally, what people would actually do is just say, I only need band 123 and 45. And those two alone, I can do some simple arithmetic and thresholding and get good results. Nowadays, it's more common to use things like transforms that separate the data into the principal components, so you really get the strongest signals that matter the most for this particular image. There's a lot of different techniques for this, things like PCA, ICA, NMF, MNF. Basically, you can take any data, no matter what dimension it's in, and you can reduce it to 2 or 3 dimensional space, and it's much easier to work with. But this is slow, so that's the downside of this, unfortunately.
Hyperspectral data when I then reduce it again.
Yeah, that's the counterintuitive thing, right? Like we purposefully recorded all of this information, but not all of that information is useful to you as opposed to someone else, right? So if you are only interested in studying roof materials, and there's like 5 different roof materials that you're trying to understand, how common is clay roof versus shingles versus other types of roof materials, and how does that influence storm damage? Which roofs are most likely to be destroyed in a hurricane or a tornado? For your very specific niche application, there's probably only 3 or 4 spectral wavelengths that matter to you. So you don't need the rest. So if you know them, you can just use them. If you don't know them, you need to basically learn them based on what are the strongest signals that differ from each other. And if someone else is doing something like agriculture and they want to be able to map different species of wheat to see which wheat species is more common in different regions, which ones handle different climate conditions better, they would use a completely different set of bands. But again, they don't know which ones to use ahead of time. So that's where this comes in. We've created a problem by solving a different problem. Now we have too much data. The other trick that you can use, and I really do call this a trick because it's really cool how it works, if you've got low resolution imagery, some of your pixels are going to be pure. So like if you're looking at agriculture, the middle of a field, every square meter of this pixel is maize or soybean. You'll also naturally have mixed pixels. The edge of the field, especially when you have low resolution, like a whole city, might be just one blurry pixel. What you can do is a trick called spectral unmixing, where you decompose the signature into end members. So for example, in the image on the right, we've got a pure blue pixel and a pure yellow pixel, and then some green pixels where there's a little bit of both. If we know that those green pixels are the result of blue plus yellow, which you can do with math, then we know that those are mixed pixels. And we can also estimate the fraction of those mixed values in each. So you can use something like the pixel purity index to identify extrema. Those will be our end members, those will be our pure pixels. And then we can use estimation to gather how much of those mixtures are in those mixed pixels. If you've ever seen a Fourier series, where you've got a complex signal and you can break it down into simpler sine and cosine waves, you change the wavelength, you add them up, and you eventually get any arbitrary function, it's the exact same idea except with light waves instead of sound. And then the last thing that you might want to do is spectral matching. So this is more of a classical technique, less of an AI technique, but you can basically take specific things that you're interested in, and you can take hyperspectral images, often in a lab, that are very, very precise, and you create basically a whole database of materials and what their hyperspectral signature should look like. And then you can take your actual recorded data and you can match it to the material that it most likely is. Now there's a lot of problems here. You can imagine that there might be atmospheric effects that distort things, noise that gets added, mixed pixels that make things a little bit more complex than this. That's hopefully where some of these other techniques or deep learning comes in. But this is what people have traditionally used to avoid some of the unknowns of AI and stick with the pure physics-based approaches. Okay, we're at a really good stopping point. So let's take a break for 7 minutes and restart at 4.
Unfortunately, I also have to leave in half an hour.
Okay.
Just for your info, because I have to go to Garching. It's like 1.5 hours from here.
Okay.
So just for your info.
Well, let's get started now then and try to finish as much as we can in 30 minutes.
Sounds good.
I think I can go quickly, and if people complain, they should have come to lecture.
Yeah.
And there's also...
I'm quick. I can be
Yeah,
quick.
perfect.
Yeah.
So we're going to restart now and try to finish early today. If people want to see the more nitty-gritty details, you can watch the recording from last semester where I do the same things a little bit slower. So this is where I show you how to actually do the preprocessing. A lot of this is using things like GDAL on the command line. Now, there's 3 different notations that I'm going to show you today. The top one is the oldest one. So if you've been using GDAL and you want to make sure that your commands work for everyone, regardless of what version of GDAL they're using, this top line, these commands have been around for decades. So these are the traditional methods for using GDAL. The traditional methods are often very confusingly named. Sometimes there's an underscore, sometimes there's not, sometimes there's a .py, sometimes the different flags or the order of things are different from one command to another. So the old interface is very stable, but also very confusing. So Newer libraries like raster.io built their own interface on top of GDAL, so replacing some of these commands and making them more uniform, making some of the names more sensical. And then even more recently, if you're using GDAL 3.11 or newer, there is a brand new GDAL CLI that fixes all of the problems with the old CLI, makes everything very uniform and easy to use. I'm going to be mostly showing that today, but I'll show the older versions of these commands as well. So I showed you this one before. You can just run GDAL info on a file and you can learn a lot of metadata about the file. There's also a lot of other flags that you can pass to this command to get more detailed information, such as statistics on mean, median, mode of your data. So let me actually show some of these on the command line. Let me make this bigger. Still very small. Okay, that's good enough. Okay. So I've got a bunch of data that I've already downloaded ahead of time. Some of this we downloaded 2 weeks ago, so there's our Landsat data, our Sentinel data. CDL is another one. So if I go into this CDL directory, this is this is a land cover mask. So this is not an image of the Earth, this is a map of the Earth. I can actually load this in QGIS and we can see what this looks like. Luckily, I already opened this ahead of time, so it's quite fast. And one correction from last week, they actually do now have native ARM64 binaries for macOS, so it is much faster than the older versions of QGIS. They're on 4.0 now, which is really exciting. These are in documents. You get to peek into my entire file system. Data. CDL. And there we have a map of the US with detailed agricultural information at 30-meter resolution for the entire country. So you can see every single field, approximately which ones are growing what. In this image, this yellowish gold color is maize, this dark green is soybean, this light gray is urban, this blue is field, this kind of light greenish bluish hue is grassland, so nothing is growing there. And the Midwest, the middle of the US, is almost exclusively either corn or soybean. So this whole region is where most of the corn comes from in the US. Other places have completely different things. I think red might be cotton. There's a bunch of different colors here. You can see the Mississippi River Delta has a lot more diverse agriculture, but those are some of the dominant crop species in the US. Now, if I run GDAL info on the same file, there's actually several files here. There's .tif, tif.ovr, these aux and aux XML files, those are actually made by QGIS, so those are temporary files. The main file is TIFF, and then the TFW has additional metadata. I think the OVR also has additional metadata, but TIFF is the main one, so we'll do geoinfo on our TIFF file. And we'll also add this stats flag to compute information about the data. And we get this as output. I'll scroll back up to the top. So again, I've shown you this before. GeoTIFF is the file driver. Good, we know how to read this one, easy. This is the image size, 150,000 by 100,000 pixels, so very large image. It is in this Albers equal area projection. So very different than some of the other ones that we've previously seen in UTM zones. And it's specifically one centered around CONUS, continental United States. So it doesn't include Hawaii, but it's centered around the main parts of the US. This is a shorthand code for the same thing that we'll see later. The units are meters, that's good to know. The origin in meters in this coordinate system, pixel size, etc. Various metadata here. The interleave is band, not block. So this would actually be very slow to load for machine learning. We can fix that later. We've got the coordinates here. This is our statistics. So the minimum value is 1, the maximum value is 254, so it's uint8. Should say that somewhere. Byte is uint8, so it's 0 to 255. Those are possible values. Mean, standard deviation, these don't really make sense for categories, but we do have that information. More detailed statistics, histogram, binning values, etc. And then this specific data set has a color table associated with it so that when you load it in QGIS, it actually has specific colors for specific things. It's not grayscale. So that's one of the differences between this and some of the satellite images we saw before. And there's also this attribute table that tells you what things are. So you can see, for instance, 0 is background, no data. 1 is corn or maize. 2 is cotton. 3 is rice. 4 is sorghum. 5 is soybeans. These are just the most 5 common things growing in the US, but it goes on forever.
The metadata is already included in the file.
I think it's in the TIFF OVR file.
So you just,
But when you do GDAL info on the TIFF file, it knows that this OVR file is additional metadata for the TIFF file, so it loads both. So it's a very smart, fancy driver that combines all these different metadata files. So that's our GDAL info command. We also might want to convert between different file formats. So if I've got something that's in IMG format and I want to convert it to TIFF, or the other direction, I can do GDAL translate, which is the old style. I can do Rio convert or GDAL convert. And that's what the syntax looks like. The input file format and the output file format are both optional. Most of the time they can figure it out from the file extension. Once in a while there's like really confusing names where it's .tiff all caps or I think it actually knows how to do that one, but like you can imagine that .img is not unique. There might be multiple things with that same file name. So you can override it if it's wrong, but most of the time it's right and it figures out what the file extension should be. And then I also mentioned we might want to rewrite our data to use blocks instead of rows. That's what this tiled equals yes is. So these are various creation options, and these are specific to the driver. So GeoTIFF supports this. Other things might not support this. This is not really a GDAL convert option. This is specific to GeoTIFF and many other file formats. For all of these, you can run GDAL -help or -h, and it will tell you what the various commands are. So there's a couple, most things are either raster or vector, so that's the GDAL versus OGR history. And then many of these also have shortcuts at a top level. So you can convert file formats from one file to another using GDAL convert, but that's really just a shortcut for GDAL raster convert or GDAL vector convert. It has to stay within that, so you can't do raster to vector or vector to raster. There's a different command for that, and I'll show that later. Driver specific stuff, again, info. GDAL info is just a shortcut for GDAL raster info or GDAL vector info. And then for each of these subcommands like GDAL convert, you can also see the options available to that. Convert -help. -help has more output than -h. So that's that Git also uses a similar pattern that might be confusing to some people, but you can get more details. And then also all of these link to the website documentation, which is convenient. So many of these also come with examples that most of the time your specific example is within this subset. So here we're converting it to a GeoTIFF, but we're specifically converting it to a cloud optimized GeoTIFF. So that one has the blocks that we need to load quickly. We also want to specify a compression option. So this would be one example. You can also convert between different file formats with this. And there's the detail we saw from the command line. So that's file format conversion. Another thing that we've already seen is mosaicing. And this is where I say the old GDAL interface was kind of confusing. We used to use GDAL merge anytime we combined files. And it didn't matter if we were mosaicing many files together to get a bigger map, or if we were stacking files across the spectral axis or across the time axis. All of it was GDAL merge. Raster IO split these into Rio merge and Rio stack, and then the new GDAL interface changed these to GDAL raster mosaic and GDAL raster stack. But we've already done GDAL raster stack in 2 weeks ago. That's how we made our RGB image. You'll also be using that on this week's homework assignment. Reprojection is another important one. So if you've got 2 different files or a million different files and they all have different coordinate reference systems, you need to reproject all of them to one shared coordinate reference system. Otherwise, one image will be warped with respect to another and they won't line up. So we can use something like GDAL warp or Rio warp or GDAL raster reproject. And again, it should be able to read the source CRS automatically. If it can't, you can tell it what it is with all of these commands. But most of the time, you only need to tell it the input file, the output file, and what CRS you want to change to. Similarly, if you want to crop an image, you've got a gigantic 10,000 by 10,000 pixel image, and you want to chop it down to 100 by 100. You can use GDAL warp for the same thing. You're not actually warping, you're cropping, so that's a little bit confusing. Or Rio clip or GDAL raster clip, and just give it your bounding box. Here we have resampling. So again, if you have data in very different resolutions and you want to resample everything to be the same resolution, you can use, again, GDAL warp, which again, not everything is a warp, but yes, it is a change in affine transformation of the data. But now there's a new GDAL raster resize command that's more specific to this actual application. And if you want those nice target aligned pixels where things line up for every grid cell, not just the same resolution, but an overlapping grid, you can use GDAL raster reproject, and you can ensure that there's target aligned pixels. Spectral indices, this one's really fun. So let's say you want to calculate something like NDVI from the command line. You can actually do this directly in one line of code and generate a new image that is NDVI. You can do GDAL calc. We have 2 input files, near infrared and red, or 2 bands of the same file, which is the top example. So I can specify what those letters mean, and I can specify my output file name, and then I can specify the math that I would like to calculate. And it literally works like a calculator. You type this in and you get your output file, which is pretty cool. Raster IO does something really strange that you've probably never seen before in your entire life. So this should look very confusing and not make any sense at all. This is functional programming. And we're going to see this again next week, so I wanted to mention it briefly now. When you think about something like addition or subtraction or division, you think of that as an infix operation, 2 plus 2. But you can also think of addition as a function that takes 2 inputs, 2 and 2. So in the raster IO example here, I'll zoom in. In the raster IO example here, everything in parentheses is done first. So the first thing that we do is we read file 1, band 1, and we read file 1, band 2. Then we add these 2 bands together. Then we divide them by 2. Same here, we first read file 1, read file 2, read file 1, read file 2. We subtract these 2 things, we add these 2 things, and then we divide these 2 things. So it's very unintuitive, it's very counterintuitive when you look at it, but it's really cool that you can use functions in this way. And it doesn't matter what the function is, you can do file reads, you can do more complex operations as well. So this is inspired by Lisp and other functional programming languages. We will, for better or for worse, see this same kind of syntax again next week when we do cloud computing. It's not very common in math or in programming, but there are actually quite a lot of programming languages that do things like this instead, where everything is a function, including addition. The other thing that you might want to do is you have a raster prediction. You've made a map of the Earth. You would like to convert this to a vector because you know that squiggly diagonal line, that's actually a straight line, and this squiggly rectangle is actually a normal rectangle. This is a field boundary or this is a building that you would like to convert to a vector representation. You can use a command like GDAL polygonize or GDAL raster polygonize to convert your GeoTIFF, your raster file, to a vector file format. This assumes that things are already grouped. So like if you can't use this on a raw image because every pixel is slightly different. But if you've got a rasterized classified map, then you can chop things into polygons quite quickly. Now, you might be asking, why are we learning all of this? Can't more of these complex tools just do all of this stuff automatically? So this is from a paper that I did where I was trying to build a software library to do all of this very quickly. And what we found was if you correctly use GDAL's cache and you pre-process the data beforehand, you can actually sample data for machine learning training orders of magnitude faster. If you don't do this, it'll still work, but it'll be very, very slow. So doing all of these pre-processing steps ahead of time can actually make machine learning much faster. And if your machine learning tool isn't doing this automatically for you, it won't work at all unless you do these things. So that was all how to pre-process raster files. For vector files, things look similar, but also a little bit different. So there is a different command for vector files called OGR. So now we have OGR info instead of GDAL info. We can do the same thing with Fiona. We don't have to use raster.io, so we can do Fio info. Or again, the new syntax is more aligned, GDAL info. I'm going to show you one file that I downloaded that you'll actually be using on your homework later. So that will be convenient. This is the Eurocrops dataset. We'll be using this for this week's homework assignment. You can find it at Zenodo. The link is in the homework assignment, or you can squint and look very closely and type that long number. And this is a data set of agriculture for the entirety of Europe, at least these countries that have this data publicly available. So you can download any one of these zip files, and that contains the data we need. This is for Austria. I'm guessing this is Belgium. Germany's split up into like 3 different regions because they don't have data for the entire country. But I already downloaded this ahead of time. So I can go to my Eurocrops directory, and you can see a ton of different files here. I'm going to do GDAL info, DE, EC21, and I'm going to focus on the SHP file. So again, this is the main file, the SHP, that's the shape file. DBF is quite similar to the OVR file we saw before. That's where it actually stores things like tables and meaning. PRG is the projection. I can't even remember what SHX is, but these all belong to one SHP file. So I'll do GDAL info on this file, and this is the information that it tells me about. So we're using the ERSI shapefile driver, good. Metadata, it was last updated in 2024. There are 2,700 features or polygons in this file. This is the spatial extent. This is the projection. It's in UTM zone 32 north, which is again very different from the image that we might happen to download. That's the short code, EPSG, and it's in units of meters. There are several different attributes stored in this, so you can think of this quite like a pandas data frame. For every field, every row, we record all of these columns. So we record the field ID, a unique number for that field. I don't remember what Inspire ID is. Some of these are country specific. This is the area in hectares. This is Germany specific, so this is the type of agriculture there. This is the thing that they added to these data sets. This is the unique, consistent mapping. They took data from all of these different countries across Europe. They harmonized it so everything has the same numbers representing the same crops. And that's the value added of this data set. So this is just a general description of the data. We can also print the data directly and see what's in there. Let me shift some things around. So we can also investigate a specific layer by using -- layer, by using -- features to see the entire data set. So if I do this, I think I can do features, and this will print the entire thing, or I can just do limit and then tell it how many I want. Most of the time I don't actually want all of them. So here's the first 10 fields, basically. So we still have that same metadata at the top if we want to look at that. And then for each field, we have some sort of integer ID. That's the number of the field, doesn't matter. Total area in hectares. This is Grunland, which is grassland in English. Great. So we've got one English representation for all of these different countries, and a specific number that is unique to this crop type. So if I wanted to rasterize this polygon, which you need to do for your homework, I would either want to use this number, which is pretty long, so I might need to shorten it, or depending on the country, some countries have a separate number for only their country, but that won't work for every country, but this one will. Hopefully that answers that question before the emails start pouring in. This is the polygon that shows the actual bounds of the field in detail. So it's these XY points to get the resulting polygon. And then there's a bunch more. So these are mostly grassland. Is there anything different here? This is maize or corn, specifically silo maize. Grassland, grassland, sugar beet is another one. Maize, winter soft wheat. So there's many different species in this area. I can also load this in QGIS. Let me get rid of this one first because it's going to be a completely different location on Earth. Hero crops. I just want the original. Oh, that's my cropped version. Where's my original version? I guess it's in this folder. Yeah, this is for the whole region of Germany. And you can see in this particular view, this is not particularly informational. We're not really learning anything other than where the fields are. We can edit the metadata for this to make it a little easier to visualize. And this is where I might need help from you because I always get lost here. So we can go to, this is the text label. I want to change the color first. Simple fill. I should be able to do this based on name. Simple fill, centroid, geometry, line, raster, species. No, that's not right. Is there a classify? Here we go. Categorized. Random colors, but we'll do it based on value. We'll do it based on this unique class. Don't know if red is a good thing or a bad thing, but let's try. We can click classify and apply. And now different species of agriculture have different colors. So that's good. That's one thing that we can do. The other thing that we can do is add text labels. We can add a single label, and we can label it based on something like the English name, which I think was N. Let's try this. Apply. And if I zoom in, we will see labels for every single field for the entirety of Germany. You can do this for all of Europe. You can do this for all of the US. Most countries don't have this amount of data available, and this is actually much higher quality than the US data. But yeah, so this is what you'll basically be doing on the homework assignment, is making these kind of maps. This is your training data, then you make a new prediction using the original data. So that was our vector file. The other things worth showing are conversion. So instead of GDAL translate going to OGR translate, now we have OGR to OGR. So completely inconsistent naming scheme, but now it's GDAL convert, same as for raster files, very nice. If you want to combine many files, OGR merge, or GDAL vector concat, you just give it the list of files and the output file. Reprojection, GDAL vector reproject, same as for raster files. You just specify the output CRS. And if you want to go the other direction from your vector file to a raster file, which you'll need to do for your homework assignment, you can use GDAL vector rasterize. This is also a place where it's a little confusing because depending on what you look at, GDAL rasterize is a GDAL command, RIO rasterize is a raster.io command, but rasterization is really something that acts on a vector file. So it's GDAL vector, not GDAL raster. So GDAL vector, rasterize. Start with vector, go to raster. Okay. Let me quickly finish this. How much time do you have left before you need to go? Okay. I think we can get close. So other things worth knowing about that you might encounter, especially in later homework assignments in this course. There's often situations where you have missing values in your data. So one of those is something like sensor failure. And a really funny example of this is actually with Landsat 7. So Landsat 7 has a push broom camera. So the camera actually goes back and forth across the Earth. And then there's a little tool that makes it swivel up and down so that you get coverage on the left, not coverage on the right. With Landsat 7 and only Landsat 7, this little tool broke and they couldn't fix it because it's already up in space. So as a result, the middle of the image looks great. We have all the information we would like. As you get closer and closer to the edge of the image, you get more and more no data pixels. You get striping as a result of this feature being broken. So we might want to do something about these missing pixels. When you read the data, there's many different ways to represent missing pixels. Sometimes it's -9999, sometimes it's 0, sometimes it's nan, sometimes it's some other no data class. And you can fill it in many ways. You can just use some constant value for everything, maybe 0, maybe not. You can use nearest neighbors, so what is the closest physical location? Let's just pretend it's the same. You can do more fancy polynomial things, or more properly, you can use time series information from a previous coverage of that same region. I believe this is, I can't remember if this was deep learning or not, but there's also a lot of research in deep learning for gap filling. Again, you have to be very, very careful here that you're doing things correctly. It's very easy to hallucinate something. It is very hard to hallucinate the right thing. So there's a lot of work that goes into ensuring the quality of these gap-filled products. Another thing that you might need to do is encoding. So when we have categorical outputs, that multi-class classification, that's very easy to do. What if we have categorical inputs? Our machine learning models can only handle floating point or integer inputs. We can easily convert these things to numbers. Corn is 1, cotton is 2, etc. But we cannot use these as inputs naively because cotton is not corn times 2, and sorghum is certainly not corn times 4. There's no numerical order to these things. There's no relationship. These are not numbers. These are categories. So what we do instead is something called a one-hot encoding. You saw this in the last homework assignment for the soil type data. You basically just have a vector of zeros where one thing is 1 and that represents the category. And now corn is not soybean divided by 4 or soybean divided by 5, I think. Now it's actually completely unrelated numbers that represent this. And this is also how people traditionally handled text data. There's fancier techniques now for that, where you can do not sparse encodings, but dense encodings, but we'll see that again in the foundation model lecture. Cyclic encoding, we already did this on homework 1, right? You didn't know what it was called, you didn't know why you were doing it, but this is what it is. If you've got time information, the first day of the year and the last day of the year numerically are completely different. 1 and 365 are not close. But if I do sine and cosine of both, all of a sudden they're approximately the same number. So we need to do a cyclic encoding for cyclic values. We do sine and cosine or a more complex representation for dealing with this. And then you always have continuous data regardless of where you are in your time series. And then the last one, and this is probably the most important one because you need to do this for many lectures, for many homework assignments, is normalization. In scikit-learn, they also call this standardization, and they're like standardization and normalization are two different things. But in the machine learning world, everyone kind of uses these interchangeably, so don't worry too much about the difference. Again, most of our models are making a lot of assumptions. They assume that we have a Gaussian distribution as input. And usually that Gaussian distribution in the real world never occurs, so we need to get our data into as close of a Gaussian approximation as we can. There's several different ways that people do this. I would say the first one, this mean standard deviation normalization, this used to be more common, especially when we were using things like sigmoids. The second one, where you go min-max normalization, and you end up with things in the range of 0 to 1, this is now more common when ReLU is the more common method. These sigmoid and ReLU things, don't worry about these for now. We'll talk about these when we get to deep learning in 2 weeks. But you do usually want your data to be normalized before you do machine learning model training. All of the scikit-learn models that we're using so far, they're doing this for us automatically. We didn't even need to ask them to. They're doing it for free. PyTorch does not do this for free. You have to do this. So when we get to the deep learning stuff, don't forget to do this. If your model is not working, this can quickly and easily help. The other technique is histogram equalization. So most images that you record, you'll notice there's a lot of background color or very strong signals in different wavelengths. You can actually slightly shift things around to get more contrast in your image, and this is exactly how things like Adobe Photoshop work. So this is also very beneficial for machine learning. This is usually kind of slow and time consuming, so people don't usually do this. They usually just do min-max normalization. And it doesn't have to be exactly min-max. You could do like 2% to 98% to avoid outliers and just clip off anything else. So this is very common in every machine learning pipeline.
QGIS does this per default. Right?
Yes, exactly.
98%.
Yep. Especially because like when you're loading images with QGIS, you have absolutely no idea what range the numbers could be in. Like traditional images are usually 0 to 255. With satellite imagery, it could be anything. It could be floating point 0 to 1. It could be 0 to 60,000. So you kind of have to do something. And it does that 2 to 98% by default because that's a pretty good default if you want to avoid outliers. Also important, when you compute things like min, max, mean, standard deviation, compute these on your training data, not on your test data. Otherwise, you're cheating a little bit and you're peeking ahead to what the data representation might look like in the test set, which you don't want to do. Okay, wrapping up, here are all of the things that we covered today. Here's links to those videos if you want to watch the third one. Here is really good documentation on the new GDAL CLI. There's also a really nice YouTube video where they talk about all of the problems with the old CLI and how they built the new one. And then the Raster.io and Fiona CLI, I didn't cover those in much detail, but you can find documentation for those. And GeoPandas might be useful for the extra credit, so you can start looking at that as well. This is a teaser for what homework 4 is going to look like. So basically you have a satellite image and you have labels. Your goal is to train a model to go from image to labels and then make labels for a region where you don't have labels. So I'll show the homework in a second. For the next lecture, we're going to be getting into cloud computing. For next week, we will specifically be using Google Earth Engine for the homework assignment. So make a Google account with Google Earth Engine if you don't have one yet. And then the entire second half of the course is deep learning. It really, really benefits to have a GPU. There are free GPUs on Google Colab and Lightning Studio. Make accounts for those for the second half of the course. Do you have to go now? Or 2 minutes? All right, let's see what we can do in 2 minutes. So this is this week's homework assignment. I really don't want you to miss your bus because I know exactly how long you have to wait if you miss it. This is our homework assignment. We're doing semantic segmentation. Again, just like with homework 2, if you're doing a command line tool, you can either put it as a comment or you can use this pound symbol, this exclamation mark, to run it directly in your Jupyter notebook. The other suggestion that I have that everyone skips that is really important, when something goes wrong, visualize every single step of the process. After every command you run, load it up in QGIS and make sure it looks like what you think it should look like. That will solve 90% of emails. The other 10%, please email me and I'm happy to help. The other thing I should say about this homework, this may or may not be the hardest homework of the semester. If you survive this homework, everything else after this is actually going to be really easy because I want you to start transitioning to your final project. So homework 5 through 10 are actually like boringly easy. It's a lot of copy and paste from tutorials and mix and match things. This is the hard one because I want you to know the pain of manually doing the pre-processing before the later tools do the pre-processing for us. So expect this to be a little bit harder than the previous ones. It is the hardest one. Start early, start today if you can. Do not wait until the day before the deadline. You are never gonna make it. Here are all the things that you can use. You can use all of these, Fiona, GeoPandas, Raster.io. I would suggest instead using the GDAL command line because you can do everything in 1 line of code instead of 10. But if you want to do things in 10 lines of code in Python, you completely can. I just don't recommend it. So we're going to download Eurocrops, any country you want, download it from Zenodo. Let me know if you have problems. Some countries are missing metadata, but let me know if you have any issues there. And it's the zip file, not the CSV file. Download a Sentinel-2 image from the same year as your data, preferably during the summer. We're always going to be Northern Hemisphere, so summer should be obvious. And it should overlap with your image, your labels. Otherwise, you can't train a model. Different bands of Sentinel-2 have different resolutions, and they're stored in different directories. We would like to resample all of these to be 10-meter resolution, merge all of these files into one so that you have one multiband file, and then crop it to 1024 by 1024 pixels. These can be done in 3 separate commands, or you can use one long command, and it is much faster if you use one long command. So I would recommend doing it first with 3 separate commands, but challenge yourself to find a faster way to do it with one long GDAL pipeline. Same thing for your vector data. You want to reproject it to the same CRS as Sentinel-2, convert it from a shapefile to a raster geotiff. That's the rasterization step. You can use the field crop class as the burn-in value, the number you want to store, and then crop it to the same extent as Sentinel-2. If you do this for the entire country of Germany, it's going to take a very long time. If you crop it at the same time as you do all of these other steps, it will be much faster. So that's another hint there. We're going to do encoding. So these crop classes are 0 to 300 million. We want them to be 0 to 10. So the 9 most common things, you do 0 to 8, and then everything else is the 10th other class. So we're going to do 10 class classification. You're going to make a geographic train val test split. That's one of the things that we learned last week. West for training, northeast for validation, etc. Pick any machine learning model you want from scikit-learn, doesn't matter which one. We're going to do classification. For validation, I don't care about hyperparameters so much. You don't have to spend a ton of time here. Try a couple values and make it look okay. It doesn't have to be perfect. Test set, report the same things we did last week. Last step, plotting, done. So that's the homework assignment. If you do have free time, which very few people have extra time after they finish the homework, there is extra credit, which is post-processing, where you basically take your data, you use the field boundaries that we know, and you do majority voting across the field to get a nice sharp map that looks something like the one I showed in QGIS, but now it's the result of machine learning. So that's the extra credit. But it's completely fine if you don't have time for the extra credit. I do want people to spend a lot of time, especially on the first few where you're pre-processing Sentinel-2 and Eurocrops. These are usually where people get stuck. Please email me if you have questions. Other than that, that's everything for this week's lecture.